A very good morning to all the panelists present today. My name is Abhronil Paul, Research Capstone Group number 111. I worked under the mentorship of Dr. Sudhanshu Tyagi. The research statement for my capstone is Analysis of Energy Harvesting for IRS-enabled UAV Communication. The need for high-speed wireless internet has been growing, fueled by the rapid usage of devices such as smartphones, tablets, and more recently IoT-style gadgets. However, there are still many drawbacks to the current 5G architecture. Research has suggested that using unmanned aerial vehicles as aerial base stations and intelligent reflecting surfaces to enhance the coverage, capacity, reliability, and energy efficiency of these wireless networks. Still, most of the UAVs have stringent size, weight, and power constraints. We cannot keep increasing the size of the onboard battery to improve the efficiency of this UAV. Hence, alternative sources of power need to be discovered. Some current alternatives to improve the performance of a UAV are ML-based algorithms to improve the path planning, deep learning-based DQN algorithms to predict an optimized path, other green sources of energy such as using solar panels, energy harvesting from nearby RF sources, which has been discussed in detail in this project. The research objective is as follows. The first objective is to calculate the power consumption of a UAV when in flight. The second is to calculate the average energy harvested for a UAV at a certain distance or height. And last, we need to calculate the efficiency of energy harvesting to determine whether this is a suitable source for improving the UAV communication. The research methodology is as follows. First, understanding the research statement and objectives. Then we go on to literature review. Then we conduct the simulation of existing papers on MATLAB. Afterwards, we have to develop our own system model where we can do our calculations. The analyzed parameters to be calculated were also discovered after this. Once we have calculated the simulations from these using MATLAB, we cross-reference them with the calculated parameters. Finally, we go for the documentation and paper draft. The identification parameters are as follows. System model. System model refers to the model in which we will do our calculations and how the communication system would look in real life. Our system consists of one rotary UAV, k number of intelligent reflecting surfaces mounted on different buildings, and the total number of user elements to be served is considered to be n. The path loss or the free space path loss is a very important parameter to calculate the harvesting efficiency in an IRS-enabled UAV communication system. The third parameter to be calculated is the power consumption or the power required to keep the UAV in flight for a certain duration of time. We refer to the image here, which shows all the forces acting on a UAV when it is in flight. Here the T shows the rotor thrust, which is normal to the disc plane. The D is the fuel cell drag, which is in opposite direction to the aircraft velocity. W refers to the UAV weight, and theta is the tilt angle of the rotor disc. The last parameter to be calculated is the energy harvesting power. The value of power harvested from renewable sources can be formulated at various heights, and the efficiency of a UAV energy harvesting system can be defined as unit energy harvested divided by total power consumption. Here we discuss about the simulation results. The path loss from a UAV can be calculated at different heights, and after simulating we can conclude that the relationship between the two is directly proportional, that is, more the height, more the path loss. The energy required to keep a UAV hovering for a particular time interval is plotted in the graph as shown in the figure. Also, the efficiency is calculated after calculating the values of harvested energy and the input power, that is, the power required to keep the UAV in flight. We can notice that the efficiency is highest for shorter flight durations. To conclude the research capstone, the average energy harvested from a user element in the nearby RF sources lies in the range of 10 to the power minus 3 joules. Also, the harvesting efficiency varies greatly depending on the flight time and total power consumption. The maximum efficiency achieved in our calculations was 83.2%, which would be much lower in a real world environment because we have considered mostly ideal environment cases. Since the energy harvested is very low, it is not suitable for a high energy system such as a UAV base station. However, we can still use this technology as a backup power during emergencies. This is a project Gantt chart. Thank you very much.